Alright, good afternoon. So here we are yet again for another lovely lecture of ENGR 2302 Engineering Dynamics. This will be the 7th lecture in this series, and today we'll be discussing topics of impulse and momentum, and the conservation of impulse and conservation of momentum and its applications to impulse. Alright, so let's begin. Okay, so impulsive motion. Let us discuss impulsive motion. And this is found in the second half of the chapter 13 of the Beer Vector Mechanics book. So, impulsive motion. What is impulse? So first let's consider impulse and motion, or impulsive motion. So let's think about this. What is impulse? Some examples. Examples of impulsive motion. Kind of example might be something like the thrust of a rocket. The thrust of a rocket over a period of time produces a change in linear momentum. Of time produces a change in linear momentum. Change in linear momentum. So that would be one example. Again, we can get a feel for this where you have a force over a time is what produces a change in linear momentum. So something like an impact would be another example. Impact, where objects exchange linear momentum and kinetic energy. But the kinetic energy doesn't always have to be conserved, but momentum always will be conserved, as we shall see. Linear momentum. All right, moving on. Okay, so let us observe the principle of linear momentum. Let's look at the principle of linear momentum. Here. Principle of impulse and momentum, or the impulse-momentum principle, as you may have heard it described before. So what does this mean? Well, consider something like this. If you have, essentially, imagine you have an object at one moment in time. So say you have an object at one moment in time, here. It has an M1, V1. M1, or just actually M won't change, but let's say MV1. Then we add an impulse to it. So an impulse is going to be applied to this object. So this is basically the, I could label this the initial momentum, initial linear momentum. Plus the impulse will equal the final linear momentum. And this is a vector quantity. And I'll finish this drawing. So initially this object had an mv1, and then a certain amount of linear momentum is applied, or certain impulse is applied. And this would be, say, impulse from 1 to 2. Impulse from 1 to 2. And this will be equal to the integral of f dt from T1 to T2. To T2. And then this will be equal to simply mv2. mv2. And we could actually say that this is a vector. In other words, this vector plus this vector is going to equal this vector. So there's going to be this relationship here. So mv2 mv1, and impulse from 1 to 2, imp from 1 to 2, which will also be a vector. So we could treat this as a vector relationship as well. All right, so this is the basic idea of impulse and momentum. We have a initial linear momentum, a mv1, and we're going to apply an impulse, which will be the integration of force over time, and from that we can get the final linear momentum, which will be mv2, m times v2 here. All right, so let's talk about this. The dimensions of this, so the dimensions of impulse, it will have dimensions of f times t if we are using an f t dimension system, force times time, or it could also have unit if we're using the mass unit system, the mass length time unit system. Well, let's see. It would be m. It would have to have the same units as mv, so it would be m. Let's see, m l t to the negative 1. Because that would be basically meters per second times kilograms if we were looking at units. Then I could also mention the unit. I could also mention the units as well. So the units for, at least in terms of metric units, are going to be Newton seconds or kilogram meters per second. Kilogram meters per second. And then some other notes on here. So let's look at Newton's second law again. So Newton's second law, I want to get some things from Newton's second law. From Newton's second law, the force vector is equal to d dt of mv, where of course mv is the linear momentum. Where mv is linear momentum. Linear momentum. From this, we could also split this up and say d, f dt, is equal to dmv, which I could then integrate and get the integral t1 to t2 of f dt is equal to mv2 minus mv1. Minus mv1 here. Or I could say, I could define the impulse as the difference between the two velocities. So I could also say the integral t1 to t2 of f vector dt is equal to impulse, the impulse from 1 to 2. The impulse, if I can manage to write a p properly, from 1 to 2. This is the impulse of force F. Of force F. Of force F. Or I could also say m v1 plus the impulse vector, so maybe I could make that a vector here, plus imp 1 to 2 is equal to m v2. So the initial momentum vector, linear momentum vector, plus the impulse vector will be equal to the final linear momentum vector. Okay, so that's fine here. So let us define something that we call impulsive force. What do we mean by, I want to define something called impulsive force. Impulsive force. Impulsive force Essentially, what I mean by an impulsive force is a force that acts on a particle over a very short period of time, a short time interval, but is still large enough to cause a significant change in momentum. To cause a significant change in momentum. A significant momentum change. Still large enough to cause a significant momentum change. And here, and so usually when we're talking about an impulsive force, we're considering something that would be a constant force. So you could have an object here, let's say you had something like this, and like this, and we show 3 instances. So say we had a ball being thrown or a ball being hit by a bat or something like that. And so you would initially have an mv1 here. Then we added to this a impulsive force, F delta t. And then downward we had the weight times delta t. And this would equal mv2. Anyone see a problem with this? I know I don't always draw my drawings to the right angles or the proper scales, but this should be pretty jarring. Namely, I have a force that's going to the left, I have a momentum that's going to the left, and I have an impulsive force that's acting to the right. But what about but then the final linear momentum is going also horizontal. What happened to this? Where'd this go? The key word is that I'm saying that an impulsive period is acting over a short time. That's the key thing. So for something to really be an impulsive force, I want it to be acting over a very short period of time. And as such, this weight delta t is approximately 0. So this force, the weight of this ball, let's say the weight of the ball is a Newton, 1 Newton. But the force that I'm exerting this to this ball might be 10,000 newtons or 1,000 newtons or something really large like that. It's just that it is acting over a short period of time, so the total change in momentum is not massive. It's not going to the moon after this. But it's simply, when this is over a very short period of time, because the weight itself is not a massive force, it is not an impulsive force. It is, when time is very small, the change in momentum produced by weight will be very small. In other words, another way to look at it for flying objects, if you have a flying object subject to an impulsive force, that impulsive force is going to absolutely dominate the force of gravity in terms of change in momentum over the collision period. So, we can also say, when an impulsive force acts on a particle, an impulsive force acts on a particle, well, we don't need to do the integration of force anymore. We instead can simply say mv1 plus summation of forces delta t is equal to mv2. See, the force, well, at least if the force is constant, we'll simply add up any of our impulsive forces, and because this acts over such a small time period, we'll generally consider them something that is constant, or more precisely, look at them average. So again, a good example would be something like a baseball being hit by a bat. The actual collision, think about how short that collision actually is. That collision might only take place over a quarter or a tenth or 100th of a second. It happens over a very, very short period of time. You would need something like a stop-motion camera to actually capture, not a stop-motion camera, is that the right term, stop-motion camera? A high-speed camera at least, to capture the motion of that ball, or the actual collision. Anyway, and from this I could also in turn define non-impulsive forces. Well, they're going to be the opposite. Non-impulsive forces are those where F delta T is small. And thus their impact may be neglected for short-term events like collision. May be neglected for short duration events like collisions. So if I am doing a problem where a baseball is hit by a bat, something like that, car crash, any kind of thing where objects are quickly colliding, I don't actually need to worry about things like the weight of the object, because it's not that it is not that weight or that force doesn't act on the object. It's that the time interval is so small relative to the size of the force, or the force is not large, so it will not produce a significant effect over tiny time intervals. Okay, so let's work through a quick example of the basic ideas of impulse. So let's look at this. I have an example here. Example. Well, so given a car weighing 4,000 pounds is driven down a 5-degree incline. At a speed of 60 miles per hour. And this will look very similar to an example we looked at previously. Previously we looked at this in terms of energy, but now I'm going to look at it in terms of momentum. At a speed of 60 miles per hour. I covered that in the previous energy video. 60 miles per hour when the brakes were applied. When the brakes are applied. Then the brakes have a force, have a braking force of 1,500 pounds. Did I really misspell brakes? Oh my. The brakes, a braking force. Still recovered from the weekend. That sounds a lot worse if you don't know the context of it. Steel bridge competition. I wasn't that partying all weekend. Anyway, 1,500 pounds. So the brakes have a braking force of 1,500 pounds. All right, so that's given, and find the time required for the automobile to stop. The stopping time of the automobile. And this is one crucial difference of momentum versus energy methods. I was going to say the stopping time. In the energy methods, we don't actually know the time, at least with direct energy methods. We can find them using Newton's second law, but using energy methods alone, we cannot find the stopping time. We can find the stopping distance, but we cannot find the stopping time. Here, we want to use impulse to find the stopping time. All right, so let's do that. So solution. So I'm going to apply the principle of impulse and momentum, and it's all going to be based off of my previous equation, mv1 plus the impulse from 1 to 2 will be equal to mv2 here. And let's say I did this here. Now in this case, I can't ignore the weight. This isn't a collision type problem, so weight is actually just going to be driving this entire thing. So I can't simply ignore that. So let's look at this here. I'm going to look at this I'm going to sort of draw the car as a block and consider three things. This is going to be my impulse, and this will be my final momentum. The car will be going on an incline. Initially it had, and I'm going to draw this exaggerated, mv1, and then later it has a much larger mv2. And then I'm going to have some forces on here. First I'll have the normal force, the weight, which will be mg, or just the weight. I don't have the mass, I'll just leave it as weight. And this will be at an angle of 5 degrees from the vertical. Actually, no, it won't. Sorry, from the incline. It'll be 5 degrees from the incline. So that would mean this here is also 5 degrees. And then the normal force will be perpendicular to the incline. So F normal. And then I would have the, let's say the force driving this, essentially. Okay? And this thing is not, actually, wait, I probably shouldn't draw this like this. I should probably draw this more like this, much smaller, because it's actually stopping. Sorry about that. What's stopping this is actually the brakes, so I probably want to show this. Maybe FB for the brakes here. FB. That's our 1,500 pound brake force. FB, 1,500 pounds. Here. And then finally, the MV2, though, is not some unknown quantity. MV2 is actually equal to 0. It's coming to rest. Okay, so considering the forces, so let's consider the forces here. Well, I want to look only at the forces, at momentum and forces along axis of motion. Along the axis of motion. So I'm going to say, so really the only force that matters will be, it will be the perpendicular component to this and the braking force here. So mv1 plus w sine of 5 degrees, that is the component of weight that will be going along the slope itself, times t minus ft equals 0. So the weight will be serving to actually accelerate the object or the car, and the braking force will be serving to decelerate it. And so that would be, let's say, did I give the speed here? Oh, yes, 60 miles per hour, yes. Okay, so I'm going to convert this to feet per second first. So this is 4,000 over 32.2 times 88 feet per second. Plus 4,000, and notice I'm even leaving the units out because they're not going to matter, they're just going to cancel out in this case, sine of 5 degrees times t. This is the only t here. Here, oh, actually, and then minus 1,500 t equals 0. And I will get the time, if you solve this, you will get the time is equal to 9.49 seconds. See, the tricky thing about this is the car is not only has to get rid of its initial velocity, its initial momentum, but by its braking force, it also has to get rid of all the additional kinetic energy and momentum that it builds up as it is braking. As it goes down the ramp, it's going to get more energy. It has to. It's going to lower elevation. So that's going to want to accelerate it. So in turn, it has to go a bit further. It's going to have to exert a even greater force therein. All right, questions on that? Okay, so hopefully that's fairly straightforward. Okay, I'll work through one other example, and then we'll move on to impact. So this one, I'm going to look at something that I'm actually going to try to find the impulse, or the average impulsive force. So a baseball, let me do given, I guess. Given, a baseball is thrown, struck by a bat, and reflected. Is that the right word for that? Sure, why not? Reflected, like it's made of light. And reflected according to the following diagram, or as shown below. So I have a bat here. So this bat is going to hit it, and initially the baseball comes in at, let's say, 80 feet per second. And this bat is both going to change the magnitude and direction of the ball's motion. So 80 feet per second, and then ricocheting, maybe that's a better word than reflecting, 120 feet per second, but also at an angle, and this angle is going to be 40 degrees. And we'll need one other piece of information. We'll also need to know that the weight of the ball is 4 ounces, just 4 ounces. All right, here. And also collision time, we are told that the collision time, maybe this was, in order to find the collision time, we maybe use some sort of high-speed camera. That would be a good way of doing that. The collision time is going to be 0.015 seconds. 0.015 seconds. And I want to find, so all of this is given, and I want to find the average impulsive force applied to the baseball. So we're not going to worry about the force of gravity acting on this thing, even though it definitely would act on the thing. We are ignoring that simply because gravity is not an impulsive force, at least in this context, the context of this problem. In the previous problem, we would have to consider gravity because we were looking at time intervals that were much longer. We were looking at approximately 10-second time interval, right? So over those types of time intervals, gravity can actually can generate significant changes in linear momentum. But something like this, 0.015 seconds, there's no way gravity can produce a substantial change in linear momentum. Well, I mean, I shouldn't say that. I mean, we don't know this thing is on Earth. I mean, if this thing were, if the baseball game were being played on the surface of a neutron star, well, then gravity could be an impulsive force, and in the time the batter swung, the ball would fall down and be traveling probably a third of the speed of light before it hit the ground, and the batter and the pitcher would be reduced to a thin layer of compressed nuclear plasma on the surface of the neutron star. But let's not worry about that. Let's not worry about such things. That may be a bit beyond the scope of this course. Sorry, I love really crazy things like neutron stars where physics goes mad. Anyway, so let's find that. Oh, and did I did put what we're looking for. We are looking for the average impulsive force applied to the ball. And note, I'm not only looking for the magnitude of that force, but I'm looking for its actual vector components. I want to know it not only as the average, but I want to know it not only as its magnitude, but the actual vector components of the force. So let's do that thing I said. Solution here. So again, we're going to come back to our basic conservation of momentum, or sorry, not necessarily conservation of momentum, but impulse momentum equation, plus the impulse from 1 to 2 is equal to mv2. Now, you might ask, or you might, if you're so inclined, you might ask, wait, haven't we learned earlier that momentum is conserved? And the thing, when you're looking at this, it might at first seem that momentum is not conserved. I mean, we have momentum here and momentum here, and then we have this thing here that's causing an increase or a decrease in momentum. And the reason that's going to work out is, in this case, the batter is hitting the ball and changing its momentum by this impulse. But the batter themselves will experience an impulse in the opposite direction, and the batter's momentum will change in the opposite direction. Now, in reality, the batter's momentum doesn't substantially change because the batter is standing braced against the surface of the earth. So they transfer that change in momentum directly into the ground, and the earth undergoes a small change in momentum. Although when they all stop and when the batter's, when the ball eventually hits the ground or is caught by a catcher, etc., then that momentum is transferred back to the earth, so the net change in the earth's momentum is 0 through the entire process. But that's okay. Now, notice I've been trying to write vector signs across all of these. And the reason for that is that these are vector components. So, what I am going to do is, because this is a vector, I can analyze it in different component directions. So I'm going to consider this in rectangular components, and I'm going to consider it both in the x direction and the y direction. So first let us look at the x direction. Let us consider the x direction of motion. Well, initially I had it was moving to the left, so I had negative mv1 plus fx delta t is equal to mv2 times the cosine of 40 degrees. So initially it was moving to the left, afterwards it's moving to the right, but at a certain angle. So I need to take the cosine of that angle to get only the x component. And then the mass here is going to be negative 4. Okay, this is going to be a little odd, but bear with me for a moment. Negative 4 over 16 divided by 32.2. I cannot do this as weight. I have to turn this into mass. So I was told that the weight of the ball was 4 ounces, and I know that 16 ounces is 1 pound. So by dividing by 16, I'm converting this into pounds. And then I divide by 32.2 to transform this into slugs. Lovely. And then plus fx, isn't the English system great? Times fx times 0.15 is equal to 4/16, same mass, over 32.2 times 120 times the cosine of 40 degrees. And if you work through this, you will find that fx is equal to 89 pounds. Approximately 89 pounds of force. Then in the y direction, well, initially we do not have any linear momentum in the y direction. So 0 plus fy, fy dt, sorry, not dt, just delta t, capital delta t, equals mv2 times the sine of 40 degrees, times the sine of 40 degrees, and this leads to simply fy times 0.15, the time of collision, equals 4/16 over 32.2 times 120 times the cosine, that should be the sine of 40 degrees, that's a typo there, 120 times the sine of 40 degrees, and therefore Fy will be equal to 39.9 pounds. So our overall F, our final result that we would report, would be 89 pounds I plus 39.9 pounds, 39.9 pounds J, here, and that's our vector form. Or I could also get the magnitude of it if I wished, and I could simply say, or I could say the magnitude of F is equal to 97.5 pounds. And that would be the magnitude of the force here necessary to cause that level of change. And that's the basic idea of simple problems of impulse and momentum. Here. So, and then let's see where we are. I think that should just about do it for what I want to cover in this portion of the lecture. Let's see what time we got. Yeah, that'll work. Okay, so let's take a short break, and when we come back, we will talk about collisions.